today we shall look into the connectivity of the graph. In fact, till today we had assumed that a given graph is a connected graph. We had assumed. You look at the instance of, let us say, I mark in your English alphabet. I has got one disconnected dot also above the I. So it is a disconnected graph that represents a disconnected graph. So there can be such a disconnected graph. For example, if you write 5, some people write 5 with the top edge as a disconnected edge. It's a disconnected graph. So if there are more than one component in the graph, then it is said to be a disconnected graph. So if there is a flow within a graph, then the graph is connected. What do I mean by flow? If I start from any vertex, and if I can manage to move to any other vertex, flowing through or traversing through the edges present in the graph, then it is a connected graph. If I cannot do that, if I cannot reach even one particular vertex starting from a vertex, then the graph has got to be essentially a disconnected graph. So if there is a flow within a graph, then the graph is connected. Else, otherwise it is disconnected. Flow is the reachability from any vertex to any other vertex traveling along the edges. That is what is the flow. All right. Therefore, if the graph is disconnected, then the graph is said to have many connected components. It will have components, and they are said to have many connected components if the graph is disconnected. So mathematically, I can express a graph as a union of several components. G1 is one component, G2 is another component, like that Gk is another component. It's a union of several components. Okay, each component is a connected graph. Each component itself is a graph by itself. Therefore, it satisfies all the requirements of a graph. But overall, there is no connectivity between G1 and G2. You cannot reach a vertex present in G2 starting from a vertex which is present in G1. Then it is a disconnected graph. Or in other words, each graph is an island by itself. They are all islands. Okay, the connectivity is not there amongst them. So it is the union. All right. Now the excellent example could be the clothes that you have immersed in a bucket while washing. They look to be connected, but they are disconnected. All clothes are totally disconnected. In fact, that is the principle based on which if you design a robot for automatically rinsing the clothes and automatically removing one cloth one by one from a bucket where you have put all clothes, then this has got to be the basic starting point, that you should understand that there are components. Each component is connected. For example, a shirt, when you take a shirt, shirt is connected, button in the shirt is connected, collar in the shirt is connected. Every component in a shirt is connected, but two shirts are not connected. The two shirts, one pant, other shirt, they are not connected at all. They are all disconnected graph units. So it is total bucket is a union of several clothes, and each cloth is connected, whereas there is no connectivity between the clothes. Is it okay? All right. Then the sigma ni, n1 plus n2 plus nk, like that, n1 plus n2, etc. nk. Sigma ni is equal to total number of vertices in the graph. Total number of vertices gni, n is equal to sigma ni. That's what is the total. Total number of edges, obviously, total number of edges is also equal to E, total number of edges. So N and D will satisfy all the stipulations of a graph. Similarly, any Ni, Ek, Ej will also satisfy the conditions of a graph. Any nk, ek, any n2, e2 will satisfy the conditions. So every component is individually a graph. One can define different types of traversal. It can be a path, it can be a walk, it can be a closed walk, it can be a circuit in a connected component. So once a graph is connected, you can think of having a walk. We will define later all these essential graph terminologies. What is a path, what is a walk, what is a closed walk, what is a circuit, etc. Not across disconnected. So definitely you will not have a path across disconnected components. You will not have a circuit across disconnected components. So now let's see if it is disconnected. If GNE, if the graph GNE is disconnected, then V vertex set can be partitioned into at least two sets of vertices, V alpha and V beta, such that V alpha and V beta are disjoint subsets. In other words, the vertices present in V alpha shall definitely not be present in V beta, and conversely. So there will not exist an edge. There will not exist an edge which has the two end vertices, one present in V alpha, another present in V beta. So there cannot be an edge so that one end vertex is in V alpha, another end vertex is in V beta. That is the definition of a disconnected component. So proceeding further, okay, what can be the algorithm? Just now I have told you, partition the graph GNE into two sets of vertices. So you recall, graph is a set of sets. One is a set of vertices, another is a set of edges. Now you take the set of vertices and partition the set of vertices into two sets, such that V alpha, one set V alpha is one connected component, and V beta may be connected or may not be connected, may be connected or may not be connected. So we should somehow partition the vertex set into V alpha and V beta, where V alpha is essentially connected, V beta may or may not be connected. Then once you get V beta gives G beta, and repeat the same procedure upon G beta till you get all partitions. So the question is how to get these vertices. You may use backtracking or you may use branch and bound, but remember the starting point is the matrix, either A matrix or X matrix. So you should start with A matrix or X matrix, and then you may start with, let us say, some particular vertex or any arbitrarily any vertex, maybe V1, and then find out all the vertices connected to V1, all vertices which are connected to V1. So all those vertices will make a set where traversability amongst themselves can be possible, and all other vertices which cannot be connected to V1 will be in the another set, V beta. So V beta, that it will be a set of vertices, no doubt, but whether they are connected or not connected is still not established. Okay, so if it is connected, starting with V1, you will get all vertices connected to V1 if it is a single component gap. That is how connectivity or unconnectivity of the gap has got to be established. Then once if you can partition it into V alpha and V beta, repeat the process upon V beta. Okay, so I have given you a simple example here pictorially. It has got three components. You can see that there are three components. This is one component, this is another component, V6 itself is another component. The algorithm should proceed like this: all vertices V1 to V9. Again, I am putting it in very abstract way. Note that you are starting with either X matrix or with A matrix. This time you cannot tell that the problems are tough, because by this time you should have got graduated to that level. You should have got elevated to that level of solving the problem. And this time I shall not consider any postponement of this assignment. I will as well ask the team to mark a 0 mark and skip this assignment if you don't want to do. It is 0 marks, that's all. Okay, you can do the next assignment very well, that's all. So V1 to V9. Okay. No problem. Absolutely. V1 to V9. All right. So now when it is V1 to V9, see, you start connectivity. When you start connecting, you will see that when you start the connectivity test starting from V1, you will see that V1 is connected to V2, V1 is connected to V4, V1 is connected to V3. All right. What about V5? But V1 is connected to V3 and V3 is connected to V5. That is why V5 is also connected to V1. Therefore, V1 to V9 gets partitioned as V1 to V5 one set and another set simply V6 to V9. We are not tested on that. We have tested the connectivity upon V1 or upon V2 and that gives this partition. Then next is you take this set V6 to V9 and maybe let us start with V6. I can see that V6 does not connect to any vertex. Therefore, V6 itself is one partition and the remaining is V7 to V9. Then I'm not still sure whether V7 to V9 is connected or not connected. I got to test that. So let us say I start with V7, then I see V8 is connected, V9 is connected, therefore V7 to V9 is connected. Therefore, there are three partitions. Okay, you can see that there are three partitions. So there are three disconnected components. The next is very interesting. Once you have got the component, disconnected component, what happens to the matrix? How will you represent the matrix? Of course, you have started with the overall matrix, but now every component will have its own A matrix, which is a submatrix. It will have its own submatrix X, and now you can therefore rearrange the entire matrix in the following way. So this contains the vertices of vertices belonging to component 1. These are the edges belonging to component 1 here. So vertices belonging to component 1 here. Look at my arrow pointer which is moving, and here are the edges belonging to component 1. Here are the vertices belonging to component 2. Here are the edges belonging to component 2. Here are the vertices belonging to component 3, and here are the edges belonging to component 3. Therefore, the submatrix A1 will be here, submatrix A2 will be here, and submatrix A3 will be here, and they take this diagonal in the entire matrix. They take the diagonal position in the entire matrix, the principal diagonal position. This is entirely zero, full sparse. This is also sparse, 0, because these vertices surely do not contain these edges, and these vertices surely do not contain these edges. Is it okay? These vertices definitely will not contain these edges. These vertices definitely will not contain these edges, but these vertices contain only these edges. So they all will be along the diagonal. Is it okay? Be careful. I'm going very slow. It might look very trivial when you are listening to that. My entire assignment, next time's assignment will be based on only this. Okay, it will be all. Then you should not come back and tell me, sir, they were very tough. No, they cannot be tough. All that it needs is common sense. I'm very sure each one of you have enough common sense to solve the problem. Okay, all right. So similarly, X matrix also can be partitioned in the similar way. Okay, these are the vertices belonging to component 1, and these are the vertices belonging to component 1. These are the vertices belonging to component 2. These are the vertices belonging to component 3. Vertices belonging to component 1, vertices belonging to component 2, vertices belonging to component 3. So the given matrix, now the question is, if I give some matrix A, and I tell that it has got 3 components, it has got 4 components. If I know that, then you should be able to permute that matrix. Is that okay? You should be able to permute that matrix, not really finding out the components present in the a graph, but you should be mathematically be permuting that matrix to get this diagonal arrangement and off diagonal sparsity. You should do that. That should also be a possibility, right? So if a matrix is said to have let us say 3 components or 4 components, you should be able to permute very intelligently. So it's an intelligent algorithm. So the system should automatically, the input to the system is that it has got 3 components. Therefore, along the diagonal, you should get 3 submatrices. Off diagonal, all of them should be perfect zeros. So you should be able to permute the rows and columns to get to this matrix. Whereas here, permuting the rows and columns are implied here. If you permute a vertex, the same vertex should be present here, because this is an adjacency matrix. This is adjacency matrix, and since it is an adjacency matrix, it is a square matrix. Row number is controlled by the column number here, whereas here row number is not controlled by the column number. But there is a relationship between the edges and the vertices. That's what you have got to exploit, and that is where you have got to do the things very intelligently. Okay, this is without really partitioning the vertices. If I give a matrix and then ask you the question, I do not know how many components are present, find out the components, then you have to go for partitioning the vertices, vertex matrix. Okay, so these are the 2 versions of the problems, which both of them are entirely different. So if a graph GNE is connected and has exactly 2 odd vertices, and both the odd vertices have got to be in the same component, isn't it? Because every component is a graph by itself, and you recall that the theorem that tells that number of odd degreed vertices can always be even, and therefore if for the entire graph which is said to be disconnected has got exactly 2 odd vertices, then it is very essential that both these odd vertices have got to be in one component. Okay, now till now I have given you the undirected version, description of undirected version to tell whether the graph is connected or disconnected. Now imagine if the graph has got directions, like if the graph has got directions, there is an arrow here, there is an arrow here, there is an arrow here, there is an arrow here. So they are all got directions. If it is a direction, then you may be able to reach V5. But from V5 you cannot be able to reach V3, because if the arrow is like this from V3 to V5, surely you can traverse from V3 to V5, but you cannot traverse from V5 to V3. So V3 is connected to V5, but V5 is disconnected from V3. If V5 is disconnected from V3, V5 is definitely be disconnected from V1 also. So this is another interesting problem. A graph may look connected. In the undirected version, the graph may look connected. In the undirected version, the matrix may look connected, but the matrix in the directed version may not be connected, may not be bidirectionally connected. Okay, so you have got to detect these components where the movement cannot be possible. For example, in general condition, the food, you know, that will go from the mouth to the stomach. The food will not should not come out from the stomach to the mouth. Okay, that's a directional movement. Therefore, mouth is connected to stomach, but stomach is not connected to mouth. So you should bring out these aspects in a connected and a disconnected graph. These are all very essential analysis in analyzing your Internet of Things later, because Internet of Things is certainly a collection of connected and disconnected graphs, and disconnected components are connected through Wi-Fi in Internet of Things. So you have got to you have got to see that the data moves in the Internet of connected network. The data moves from the printer, from the memory to the printer, from the computer to the printer, but the data will not move from printer to the computer. However, printer, if it is intelligent, can send the detail to the computer telling that the printing job is over. So the printer will acknowledge, receive the packet, it will print. After printing it, it will send a message to the originating, to the source computer, telling that the job assigned to me has been over now. That it can do that. So you have got to identify all these connectivity and disconnectivity, and it has got to be done dynamically. It is one of the real-time application, connectivity, disconnectivity check. Okay, so I'm spending more time here to tell you that there are many interesting problems. See, even now till today you have been concentrating only on your problem, but concentrating and solving your problem is not the complete journey of your study. What others have solved, how others have solved is also important, and that is also going to be assessed later. Okay, Dr. Javed will come out with a method to assess you whether you have understood what others have solved, whether you have really put your hands into seeing how others, what other problems have been there, how what are the other problems got by other your classmates, and how they have solved. Even that is necessary. Okay, all right. Okay, so now, do you recall what is the maximum number of edges in a simple connected graph? You remember that we had derived a formula that it must be half times n into n minus 1, where n is the total number of vertices. That is the maximum number of edges present in a simple connected graph. Recall what is a simple graph? A simple graph is that graph which does not have parallel edges and which does not have self loops. So it's also called a linear graph. Now, what's the maximum number of edges in a simple, of course, in a simple graph, no parallel edges, no self loops, but it is a disconnected graph having k components. If k is 1, you know that it is half n into n minus 1. So the total number of maximum number of edges in a k component graph is n minus k into n minus k plus 1 divided by 2. So we will see if k is 1, if k is 1, it's only one component gap, 1, n minus 1, here minus 1 plus 1 cancels, n into n minus 1 by 2. So if k is 1, then Emax is n into n minus 1 by 2, which we have already derived in one of the earlier class. Now, how to derive this? N minus k into n minus k plus 1 by 2, which is the maximum number of components. Please follow the derivation, and if you do not understand, you can really unmute yourself and ask me if you do not understand. Please follow it very carefully. I have already told you sigma ni is equal to n. So total number of vertices is equal to n summed up over all the k components. If I therefore remove one vertex from every component, so if I remove one vertex from ith component, then the total number of vertices that I will be removing will be k number of vertices from every component. Therefore, it will be n minus k, isn't it? So mathematically, sigma ni minus 1 summed up over from I to k component should be equal to n minus k. Okay. Now, just a bit of mathematical jugglery. I shall be squaring both the sides. This is sigma squaring under sigma sign, and this is simple squaring, n minus k squared. So squaring both the sides. So therefore, if I square it, then it will be n minus k whole square. N minus k whole square is n square minus 2nk plus k square. Whereas when you square this, you should be careful. When you square this, there is a sigma, and that gives to 1 sigma ni square term. 1 sigma ni square term. Another obviously minus 2ni, minus 2ab, 2ni under sigma sign, sigma 2ni. Another is 1 square, that becomes 1 square under sigma. Okay, 1 square under sigma. So the 1 square is 1 under sigma. Sigma k, therefore it will be k. Is it all right? Sigma 1 k times is k. All right. So it is sigma ni square minus 2 sigma ni plus lot more non-negative cross terms. Here there are many more terms also, right? This is sigma. Please note that. Therefore, there are many cross terms. In general, if I drop all these cross terms, I can tell that this summation should be less than this n square minus 2nk plus k square in general. So this should be less or equal to this. That is what I am going to write down next. So next what I have written is sigma ni square minus 2 sigma ni plus k should be less than or equal to this side. Left hand side is this. RHS is n minus k whole square, which is n square minus 2nk plus k square. You know that the variable is ni square and ni, sigma ni and sigma ni square. You know that is the variable. All right, and this is over summed up over k. What is sigma ni summed up over k? Sigma ni summed up over k is n. You know that it is n. This is sigma ni square. So sigma ni square shall therefore be less than n square. This is, it becomes n minus 2n, it goes to this side plus 2n minus 2nk plus k square minus k. Is that all right? Sigma ni square will be this inequality. All right. You can simplify this inequality if you want. You can take out 2n common here. You can take out k common here. There is a k minus 1 factor. You can keep it, or you can keep this inequality like this itself. So it is n square minus k minus 1 into 2n minus k. You keep this inequality. Let us start from some other direction. What is the maximum number of edges in an ith component? In an ith component, the maximum number of edges is half into ni into ni minus 1, isn't it? In only ith component. Expand it, half ni square minus half ni. Therefore, what is the maximum number of edges? Sigma ei max. When you take sigma ei max, it is sigma of this I going from 1 to k. So half outside, sigma of this I going from 1 to k, which is ni square minus ni. Is that okay? All right. So this means it is half sigma ni square minus sigma ni. Sigma ni is n. You know that it is half, somewhere half is last here, half sigma ni square minus n. So this half is last year of ni. This sigma ni square you substitute from here, the inequality. Is it all right? For the sigma ni square, use that without sigma, n square plus 2n minus 2nk plus k square minus k. You substitute here and do some manipulations. That's all. Just substitute and do the simplification. When you do the simplification, you will get half n minus k into n minus k plus 1. Is it okay? All right. You just do some simplification. It's very simple. Okay. All that I will give you only one hint. Here this 2nk is minus 2nk is rewritten as minus nk and minus nk, so that factorization could comfortably be done. Okay, half n minus k into n minus k plus 1. Okay, this is what is the derivation. So this can lead to many interesting results. This mathematics will definitely lead to many interesting results, and this mathematics is a bridge between your computer graphics and graph theory. All right, between the number of windows that you can see in a computer graphics with your graph theory modeling. All right. Okay. Anyhow, this is the maximum number of edges of a disconnected simple graph with k components. Okay. All right. All right. Then let us go through whether you have done it. Some of them they have done it, and some of them might not have been done by them. You just see that. Given a picture, so by this time, you should be able to solve all these problems. Given a picture or a diagram or a photograph, scan it and construct a or x representation. This is a very important robotic vision problem. This is what a robot automatically has got to do. An artificially intelligent robot has to look at, scan and construct a dependency graph, relationship graph, and analyze the relationships. Okay. I'm sure you have already done it in the first round of your assignment itself, one such problem. Okay, given your X matrix, construct a graph diagram. This is exactly again your robots, your vision system have got to do. So it has constructed a matrix, but then every time a matrix is a condensed representation, whereas a graph diagram is a diagramic representation. So definitely matrix takes less memory and a diagram takes more memory. However, from the matrix you should be able to visualize the diagram. I think I remember that I had given this also as assignment, and I'm sure you would have done it. Okay, but the point is all of them should definitely be knowing this. Okay, given a scanned or a photographed diagram with a noisy background, if the background is very noisy, such as salt and pepper noise, or ruled page where the printed lines could get mixed up as edges, then construct A or X matrix. Okay, so this is this problem also you have solved this problem also. The hand drawn diagrams may also contain handwritten labels or handwritten weights or handwritten labels. Then how will you construct the whole matrix, which surely requires little text processing also. Okay, all right. Given a hand drawn or machine printed electrical network diagram, you must have done it in your PUC classes. Why in PUC classes when you joined your first semester BTech or in second semester BTech when you did electrical or electronics course? You have done it. Diagram with values of the components written against or near the respective components. Represent the diagram as a weighted graph diagram and then represent the graph as E or X matrix. Okay. All right. I think they have not done it. All right, you just check. Okay, you just check. Now, this is construct ARX matrix for the following text matrices. Text in multiple lines. All right, the text is written in multiple lines. The text containing multiple words. A word containing characters in machine printed format. All right, the word can be containing characters in machine printed format. So every character is a disconnected component. All right. In a sentence, every word is a disconnected component. And in multiple lines, every line must be a disconnected component. Further, in a page, every paragraph is disconnected from every other paragraph. So you should see that the importance of the graph is very much there in your layout analysis or in your text analysis, text document analysis. The entire page is split into paragraphs, segmented into paragraphs. This is what is the text segmentation. The paragraph is segmented into lines, and every line is segmented into words. Every word has got to be segmented into characters. If it is a handwritten, segmenting a word into a character is difficult because it is cursive. If it is machine printed, you can easily segment. But if it is cursive, it is difficult. All right. I shall not go beyond. In fact, Dr. Javed, when he was working for his PhD with me, he worked on the same problem, but not in this statement. The further was the text document was given as a compressed file. In a compressed file, when the text document is given, without decompressing, he had to segment the paragraphs and paragraphs into lines, lines into words, words into text characters, and that too in a machine printed or handwritten document. So you will not be doing that, but then you should think of solving such advanced problems. Okay. All right. This I would be giving as an assignment this time, perhaps not up to multiple lines. Now, once I mentioned about multiple lines, I got to slightly deviate and ask you what is the difference between segmenting a paragraph into sentences and segmenting a paragraph into multiple lines? You should think of that. So a line may have more than one sentence, or a paragraph of 15 lines may just have only 5 sentences, may just have 6 sentences. So you should know the challenge between segmenting the lines and segmenting the sentences. Okay. Of course, one of the graphics method could be a sentence always ends with a full stop, or sentence ends with a question mark, whereas a line is the end of the line. That's all. It's the end of line. So let us see how you would think about it. Okay. All right.